Today I'd like to talk about velocity and acceleration. In a previous discussion, we saw that if we interpret t as time and r as telling you the location of something, then r prime points in the direction of travel, as long as it isn't the zero vector, and the magnitude is the speed. We're going to call r prime the velocity vector. The velocity vector is the derivative of my position vector. The acceleration is going to be the derivative of the velocity vector, which is the second derivative of position with respect to time. When I use the words velocity and acceleration from now on, I'm going to try to always say velocity vector, acceleration vector. If I'm interested in the speed, that's the magnitude of the velocity. If I'm interested in some sense how strong the acceleration is, I'll calculate its magnitude. For example, if my vector-valued function is r of t equals t squared I plus 4tj, the velocity vector is the derivative of that. The derivative of t squared is 2t. The derivative of 4t is the constant 4. The acceleration is the derivative of the velocity vector. The derivative of 2t is 2. The derivative of the constant 4 is 0. This is a constant acceleration because of the t squared. Letting b and omega be positive constants, this vector-valued function has a graph that's a circle of radius b centered at the origin. The omega is going to be related to how long it takes to go completely around the circle. The period of cosine omega t and sine omega t are both 2 pi divided by omega. The omega is called the angular frequency of the motion. Using the chain rule, it's easy enough to get an expression for the velocity vector. I want to calculate the speed also, which is the magnitude of the v vector. Doing a little bit of algebra, this is going to simplify nicely for me. Sine squared omega t plus cosine squared omega t is 1, no matter what t is. Also, b and omega were taken to be positive constants, so the square root of b squared omega squared is just b times omega. The speed is constant. I always ask this question in face-to-face classes, and I usually fool people. The speed is constant. You're never speeding up, you're never slowing down. Do I even need to calculate the acceleration vector? And then everyone in the room says, oh no, because the speed is a constant. Let's calculate the acceleration vector anyway and see what happens. Even though the speed never changes, the acceleration vector is not necessarily 0. How can this be? Even though in this case the speed never changes, how fast you're moving never changes, the direction is changing all the time. A vector quantity has both direction and a length to it. Even if the length stays the same, the direction doesn't have to. You can do a calculation for the magnitude of the acceleration. It turns out to be b times omega squared. The strength of the acceleration is going to be the radius of the circle multiplied by the square of the angular velocity. This lets us get to a fact that's well known to physics students. If you're going around in a circle of constant speed, the acceleration has magnitude speed squared divided by the radius. If you remain close to the surface of the Earth, the acceleration due to Earth's gravity is more or less a constant. People usually quote the figure 9.8 meters per second squared, or 32 feet per second squared. We really should do this in a fully three-dimensional setting, but most textbooks, when they introduce this topic, work it in 2 dimensions. So we will assume that any motion that goes on happens in the XY plane. In that situation, the vertical is the y-axis. I'll take the acceleration to be the vector 0, negative g, so that it points in the downwards direction. The g is either 9.8 or 32, depending on what system of units you're using. The acceleration, though, is the derivative of the velocity vector. We know how to differentiate functions, one slot at a time, so it stands to reason that we do antiderivatives in the same way. The velocity vector can be written as 0, negative gt plus a constant vector of integration. If at, say, t equals 0, I knew what the velocity vector was, it would be the value of c, d. Since at t equals 0, this vector is 0. So we can write the velocity vector as 0, negative gt plus the initial velocity vector, the velocity when t is 0. The velocity vector, though, is the derivative of the position, so if we integrate once again, we'll find a formula for the position vector. As before, there'll be constants of integration, which I'm calling alpha and beta here. We will split those out and then have an interpretation for them. If t is 0, then this vector is 0. This would be the number 0 times a constant vector, which is 0. This would be the r evaluated at t equals 0. This would be the position of the object at the beginning of the situation, at t equals 0. From a logical perspective, I much prefer this form. I'm going to work a little problem with this, then I'll also show you the form that most textbooks like to use instead. At t equals 0, some object has position vector 5, 10, meaning x is 5 and y is 10. I'll be using feet for my units of measurement and seconds for time. At that same initial time, t equals 0, the velocity vector has components 30 and 40 feet per second, respectively. I'd like to figure out where the projectile hits the ground and how fast it's going when it does so. 1/2 times 32 is 16, and since we have the initial positions and velocity vectors, I can just write down in my previous equation that the position at time t is the vector negative 16t squared in the y position, 0 in the x, the vector t multiplied by 30, 40, plus the constant vector 5, 10. The vector 30, 40 multiplied by the number t is 30t, 40t. Once I've written it in that form, 0 plus 30t plus 5 is the x component of the position vector, and negative 16t squared plus 40t plus 10 is the y coordinate. When the object hits the ground, its y coordinate must be 0, so I'm going to take the situation where this quantity is 0. This quadratic equation is going to have two solutions. One of them will be negative, the other positive. It's the positive one we're interested in, since t equals 0 was the beginning of this situation. Assuming I've typed my numbers correctly into my calculator, the t that I'm interested in is about 2.729 seconds. This tells me the time at which the projectile hits the ground. If I evaluate the x-coordinate at that time value, I find out that the x-coordinate of the place where it hits the ground is 86.87 feet. To get the speed, I need to know the velocity vector at the moment of impact and then calculate its magnitude. If I take the derivative of my vector-valued function that describes the motion, I find out that the velocity vector is 30, 40 minus 32t. When the object hits the ground, its velocity vector is 30, negative 47.328. At the moment the object hits the ground, it's traveling at about 56.035 feet per second. The way the textbook prefers to describe this situation is this. At t equals 0, at the beginning of the situation, the object is directly above the origin with height h. Also, the initial velocity vector is sometimes given in terms of the speed and also the initial direction. So v with a subscript 0 with no arrow over it is supposed to be the initial speed. It's the magnitude of the initial velocity vector. The initial angle of inclination with respect to the horizontal is angle theta. The textbook prefers to write the initial velocity vector in this format. So I can write out my position vector in the same way that we did before, except I've expressed the initial velocity vector times t in this form, and given the new setup, I put the initial position at x equals 0, y equal h. Making those substitutions, I can get this kind of formula for my position vector. So if I told you the initial speed and the initial angle of inclination, you could write down the formula for the position, you could find out where the object hit the ground, you could find out how fast it was going, and so on and so forth. This is about all I wanted to say in this section. I hope everyone's having a good day, and I'll talk to you again soon.